Hello again. In this segment, we'll be speaking again about air flushing technologies, and in particular, we'll be speaking about in situ air sparging, and I'll be speaking about the theoretical considerations of this work. So in situ air sparging, if we could expose the water table, this is how it would look. So in situ air sparging, we'll use air or perhaps ozone, a gas oxidant at the air or the ozone. It is injected into the well. The well is completed within the saturated zone. We have a phase transfer between the injected air stream and the dissolved phase. It can be operated as a pulse mode, or it could be used to inject in ambient air into the source area as a biosparging application. The general configuration of an air sparging system consists of the air injection system, an air compressor in a well, and the off gases as they migrate through the saturated zone to the vado zone are captured by a soil vacuum extraction system. You don't have to use a standard vertical well, so in some cases a horizontal air sparging well is used. Don't confuse in situ air sparging with large diameter wells, which are used to establish a groundwater circulation pattern, which is speaking about in situ air sparging and not in well stripping. From a mass removal perspective, the processes that controlling the mass removal involve volatilization, that is mass transfer from the free phase to the air phase, or from the dissolved phase to the air phase, or perhaps transfer from the injected air phase to the saturated zone, and that is again to enhance the biodegradation process. For a compound to be strippable, the Henry's law constant has to be bigger than approximately 0.0004. So compounds that are deemed to be strippable include benzene, toluene, xylene, trichloroethylene, and tetrachloroethylene. In situ air sparging has been used to treat both a source zone and a plume. For the source zone in the upper figure here, we see the source zone has a collection of air sparging wells around it. And for a dissolved plume treatment, you can see that the plume itself has been completely covered with air sparging wells, and the circumference of the air sparging well is called the radius of influence. Air sparging has also been used as part of a sparge curtain at the downgrading end of a plume, and has also been part of a funnel gate where within the gate air sparging wells are placed. The mechanics of the airflow system, in which you inject a known pressure or flow rate into the well, and that will then cause the water level within the well to decrease over time from time 1 to 4. And once the air then has displaced the water in the well bore, the air will then reach the screen zone and the local geology that will control the airflow out of the screen zone and into the aquifer itself. The pressure in the gas phase that is required to inject have to overcome the pressure loss within the piping P sub F, and have to overcome the pressure loss within the well screen P sub S. The basics behind air sparging, once the air will leave the well bore, is a classical two-phase flow problem between air and water. In this case, the non-wetting fluid is air, and that will displace the wetting fluid, water. Air is less viscous and will displace the more viscous fluid, water. air will displace the more dense fluid, water. And it's clear that air is very buoyant and wants to escape or wants to climb up as quickly as it can. So a few myths. Myth 1. Injected air will produce small bubbles that start at the sparge well and move upwards and outwards to the water table. That is incorrect. Rather, airflow occurs as a discrete channel, perhaps the size of a pen. The continuous gas phase will displace the water phase, and we have a true multi-phase flow process. From a purely theoretical perspective, if we had an air bubble, as shown here in purple, surrounded by some sand grains, if we wrote down the expression for the buoyancy force, that would have to be balanced by the capillary pressure force. And the ratio of the buoyancy force over the capillary pressure force is known as the bond number over here in right. It's been shown that a bond number bigger than 1 will create bubble flow, and a bond number less than 1 will create channel flow. And bubble flow, or a bond number bigger than 1, occurs around a mean grain size of 1 to 2 millimeters, which is quite large. So hence, most air sparging sites will have channel flow. So hence, we see, instead of bubbles, we see a random array of discrete air channel. So that sketch has been shown in the lab. On the right here is a image from an experiment in a laboratory tank. Myth 2, that in most cases the injected air is uniform and contaminant and air contact is high. Rather, since we have channel flow, heterogeneous play a very important role. So to show how this would work, I turn to some modeling work that we have done. Here we have an aquifer, a two-dimensional aquifer. The sparge well is shown here in red, and we're going to populate the domain with a range of geology that have various permeability behavior. Start off with case 1 and case 2 have a correlation structure within the permeability field that is the same in the X and the Y direction. The only difference between case 1 and 2 is case 2 has a much higher variance associated with that. And then case 3 and 4 have a much more layered structure, so the correlation along the length is highly correlated. And then case 3 and 4, case 3 has a much lower variance than case 4. The mean permeability for all of these numerical experiments is 1 times 10 to the minus 12 meters squared. So for the base case, or for the homogeneous case, we see that from the sparge point here, we see a very nice, uniform, parabolic profile of desaturated pores, as one might expect in a cartoon of how air sparging would work. Recall that this is a continuous system here, and in reality, airflow behaves as discrete channels. As the material within the model becomes more heterogeneous, we see that the air distribution pattern is not the same. And as we increase the variance between 0.1 and 0.5, you can see that the concentrated zones of higher air saturation increase. If we take that structure and make that into a structure where there's a higher correlation and permeability along lenses, so you have a layered structure, we can see now that the layered structure will cause the airflow to pool underneath a lower hydraulic conductivity until the pressure will increase and the air then can propagate through or break through that lower capillary air. If we increase that, we see something that would have the action point is here, and clearly the air is pooling below these low permeability structures and propagating laterally both to the right and the left. So what we have in a real situation then is the airflow that will leave the well stream will then be impacted by the geologic properties of the domain. If we have a heterogeneous sand system, as I said before, the air will collect underneath the lower permeability zones or higher capillary pressure zones, either fill up the pore space under the zone with air and then roll off, or enough air pressure under the lower permeability zone occurs, in which case the capillary pressure exceeds the displacement pressure of the lower permeability zone and air will migrate through it. So if we had a dense non-aqueous phase liquid problem, it would be clear that the air would go around the target area and would lead to a very inefficient air sparging system. Myth 3, that the injected air results in the production of large-scale water phase circulation cells. Rather, there is some advective water movement that occurs between setup and collapse. This is a historical myth in which these large water circulation cells would form within the aquifer as a result of air sparging. And what we have shown with some very simple modeling work is that if you look at a series of points close by an air sparging well, so this arrow here is the air sparging well, and if you were to track the water movement of a particle at the red dots, the figure on the right hand side shows the displacement or the particle tracking of those red dots during setup and collapse of an air sparging system. So let's look at this one here that's in complete alignment here with the air sparging point. It begins here, and as the air sparging system is turned on, that point then will propagate slightly to the right and down. And then once the air sparging is turned off, it will then propagate from down here upwards and end up slightly offset from where it began. And that's just based on the air sparging startup and shut down the displacement of the fluid around that zone. And you can see that if you run the system in a pulse sparging mode, there will be a displacement of fluid. So that concludes our overview of theoretical considerations for in situ air sparging. And the next segment of this will include a discussion about a pilot scale in situ air sparging study. Bye for now.